This video lecture is about database design. In particular, it is addressing the high-level design issues, not the detailed issues, which will be the subject of the subsequent lectures. The particular aspect we are looking at is a method called entity relationship modeling. You can find the major source for this material in the textbook, Chapter 6. Excluding Chapter 6.7, there will be a separate video lecture on that particular topic. Chapter 6 in the 7th edition of the textbook is actually Chapter 7 in the 6th edition of the textbook. There is no particular cross-reference material or supplemental reading to this. The primary learning outcomes of this material is that we will look at the building blocks of the entity relationship model, in particular entities, relationships, constraints, cardinality, participation, and the development of primary keys and weak entity sets. We will then study how to illustrate an entity relationship model in a diagram, and we will then look at design issues in dealing with entity relationship modeling, because there are a number of non-trivial design options you have facing you, and you will have to decide among your options. And we will conclude with talking briefly about aggregation, which is an extension to the core entity relational modeling technique. So let's first talk about what we're trying to do. We're trying to model the world. The world, at a first approximation, can be modeled as things. So things exist. There are books, there are people, there are libraries, there are companies that create products, there are companies that sell products, etc., etc. These are all things, which in the entity relationship model are referred to as entities. There are then relationships among those entities. For example, if we have Fred, and I'm generally in these slides going to use red to indicate an entity. This will not be exclusive, but in general I have tried to do this. Italics to indicate a relation. Okay? And so you will, on various occasions, see italics for relation, red for entity. So, Fred, a person, borrowed, a relationship, a book, War and Peace, from another entity, the Kitchener Library. So we've got three separate entities there. Fred is an entity, the book War and Peace is an entity, and the library is an entity. Now we can broaden that to people borrow books from libraries. This is a relationship among three separate entities. Okay, you could imagine two separate entities in a relationship. People borrow books, or two separate entities. Books are borrowed from libraries, or even a third binary relationship. People go to libraries. Okay, but this is a three-entity interaction. So let's talk a little bit more about what we mean by entities. An entity is an object that exists and is distinguishable from other objects. So let's start with, what does it mean to exist? Okay, that sounds sort of like a strange question, or a philosophical question. From a database perspective, to exist means to exist in, got that wrong, to exist in Plato's world. Okay. Plato's world is the world of ideals. Okay. Why do I say that? Because entities can exist within a database while not existing in the real world. What do I mean by that? Well, okay, all three of these entities, they all clearly exist. A specific person, a specific telephone, a specific office. And the reason I say specific in each case is because they are distinguishable. Okay, Fred is not Mary. Mary is not Muhammad. These are distinct people. Okay. But now we could talk about, okay, this imaginary course that I have made up. Okay, there's special relativity and there's general relativity. And so let's create this fake course. We'll call it very special relativity. Okay. This course doesn't exist. It's imaginary. Okay. But it exists in the sense that we have defined a course. It has a course number, department. It's in the physics department. It's 432. It has a title. Maybe it has a description. Very special relativity is all about whatever. But you can never actually take this course. This course is never offered. Okay? So, in some sense of the real world, it doesn't exist. But that's okay. From a database perspective, this course exists. Okay? This is very important. It's very important to understand because there are many things, entities that we create within databases that don't exist in the real world. For example, a course exists independent of whether or not it's ever been offered. Okay, so this is worth understanding. Okay, it is distinguishable from other objects. That's why we have specific all down here. I already mentioned Fred is not Mary, etc. No two entities are the same. They are distinct. Okay. What this means is if two things are the same, then they're not two things. They are one thing. Okay. This, by the way, is why we have sets. Okay. Every element in a set is distinct from every other element. Okay. What properties do they have? Entities have properties that we call attributes. So a person has a name, an age, a hair color, an address, etc. A telephone may have a number if it's hooked up, has a location, it has a type for Samsung telephone or an iPhone telephone, etc. So these are the attributes of an entity. Now, if we take a collection of entities that all share the same properties, we can create an entity set. So we can create the set all UWECE students. That's a set where they all share the same property that they are ECE students in the University of Waterloo. Or we could have a different set, all UW students. Now notice that this is a subset of the other. Okay, UWECE students are UW students. So sets may be related in that type of fashion, or they may be unrelated. If we go back to this previous example, books. Okay, War and Peace is a book. A book has properties like an ISBN number and a title, etc. So we can put together collections of books, War and Peace, okay, Crime and Punishment, whatever else you have in your book collection, Plato's Republic. These are all part of the entity set books. Let's look a little bit more at attributes of a book. Now, just as I use red for an entity and italics for a relation, I'm going to generally try to use green if I'm referring to specific attributes. These are descriptive properties that are possessed by all members of an entity set. So a person has a name, a height, a weight, a birth date, some location that is their home, etc. A book has an ISBN, one or more authors, a title, a page count, whatever else. Now there's a set of optional descriptive properties which may or may not be added to an attribute set for an entity. Cell phone number, hair color, spouse's name. So this requires the person to be married. This requires the person to have hair. A cell phone number requires a person to have a cell phone. Okay. A book may have a volume number, an editor, a subtitle, an illustrator, but it may not have any of these. Okay. Descriptive properties that are optional may or may not be added to an entity set. We may want to create them as part of the entity set because we're going to do a method that involves nulls or missing information for people who don't have these characteristics. Or we may say, no, these are going to go in separate tables. These are going to go in separate entities. So we could have an entity person that just has these characteristics, and we have separate entities to cover these characteristics. Or we could put them all in one. A lot will depend on our design choices, and we'll see that later within this lecture. What else can we say about attributes? Every attribute has a domain, which defines the set of permitted values for the attribute. So salary is a non-negative integer. You may say, why is it an integer? Don't I get dollars and cents? The answer is just imagine the total amount in cents. It rounds up, okay? So if you earn $100.43, that's not a decimal. Well, you would probably use that as decimal and say 7,2, but you can just as easily view that as 10,043 cents. Okay. So that's why that's a non-negative integer. A birth date comprises a day, a month, and a year. Might include a timestamp too. Who knows? But it certainly isn't a random string of characters. It has to be a day, a month, and a year, and possibly a timestamp. Hair color, defined as any element from the set, black, brown, red, auburn, whatever, and you list all your possible hair colors. Okay? Which, by the way, gives a notion of how you would handle this. For a person who has no hair, you would simply have within this set none as a characteristic, which basically says if the person has no hair, we're just going to label it as none. Okay, attributes can be single-valued or multi-valued. And this is more complex than you might think. So, some of these are unambiguously single-valued. Birth date. You don't have more than one birth date. You're born. It is whatever day it is. You may have it right, you may have it wrong, but there is only one time at which you're born. You have only one first name. No question. Home address. That's probably true. Cell phone number. Well, you may have more than one cell phone number. Middle names. Plural right there. It is very common for many databases to have first name, middle name. I should say many databases in North America to have first name, middle name, and last name. You might well have multiple middle names, in which case it is a multi-valued attribute. It isn't actually quite a multi-valued attribute because there's invariably an order to middle names. Fred, James Joseph Jones. This is the first middle name, and this is the second middle name. These are not interchangeable. So there is a reason for saying a middle name is a single valued attribute, and those people who have the luxury of having multiple middle names can arbitrarily pick one of them. Or they can join them together. They could have a middle name James Jones if they wanted. Okay. Or maybe they just put their initials in here, JJ. A multi-valued attribute. Notice I had home address here. Home address is usually a single valued attribute. For example, if you're a university student, you may have your address when you're at university and your address that is your home address. Why would this be relevant? Well, suppose you're coming towards graduation and you have some interaction and maybe you're getting a diploma, and the diploma is going to be mailed to you because there's no graduation ceremony possibly, or possibly you're unable to attend the graduation ceremony, and so the diploma will be mailed to you, but it will be mailed to your home address rather than the address where you live when you are attending the university. Whoops. Because you're not currently at the university, you've already finished when the diploma is mailed. Address itself would potentially be a multi-valued attribute because it could include a home address, an address when you're at university, maybe you have a cottage, or maybe you have a second home, who knows. A cell phone number, typically, not always, but typically you only have one cell phone. Some people will have a business cell phone and a personal cell phone, but in that particular context, usually there is a distinct cell phone number. But the notion of a phone number, well, there's the cell number, there's the home number, there's the office number, etc. You may have multiple numbers, okay? So, phone number would be potentially a multi-valued attribute. Then we have a second aspect of attributes. They may be simple or they may be composite. A simple attribute is one that is indivisible or atomic, and I've underlined this bit because it's important, insofar as we are concerned. So GPA. Your GPA is some average over the courses you have taken over some time period. It is a computed number. Yeah, but isn't it a simple number at the end of the day? Maybe my average is 87. Isn't that atomic? The answer is, well, it depends on how you're looking at it. If I want to change that into EIGHTYSEVEN, it's rather important that I know that this is the second digit, or the biggest digit, but it's in the tens columns, so it's 80, not 8. Okay, your GPA is not 87, it's 87. So if I actually wanted to do that, it's kind of relevant, potentially. Now, okay, that seems a little bit obscure, and it is a little bit obscure, but what if instead of talking about your GPA, we start talking about your birth date? That's got a day, a month, and a year. Now, there are people who study these things, and they'll study these things with respect to things like what month of the year you were born in. For example, if you look at ice hockey players, the vast majority of ice hockey players were born in January, February, and March. And that has to do with the fact that when you start playing ice hockey, the age group you're put in is determined by the calendar year. So if you're born in January and you're 5 years old, you're probably a lot bigger than a kid who's born in December and is 5 years old in that same year. So, kids starting hockey, well, a 5-year-old born in January versus a kid who will be turning 5 in December, there's nearly a year's difference between them, so these kids will be much bigger. And they'll also be better coordinated because they're nearly a year older. They're less likely to fall over when they're ice skating, etc. So it turns out this is hugely relevant. Which means for the people who are studying this, they have a hockey database and they have the birth date in the database. They don't want birth date as a single number. They want it as 3 different notions. They want the day, the month, and the year. So, do we want something broken down or don't we? And the answer is maybe we don't. Maybe it's not relevant to us. Maybe it's completely irrelevant to us. We tend to assume things are atomic or things are divisible according to how we have actually used them. But if you are a statistician studying hockey, you get a totally different thing. By the way, January, February, March is because the hockey year calendar follows the calendar year. The school year calendar in Canada, or Ontario at least, also follows the calendar year. The school year calendar in England, where I grew up, followed the August-September dividing line. So if you were born in September, you were probably the oldest kid in your class, and if you were born in August, you were probably the youngest kid in your class. How old you are as a kid in your class makes a very little difference in university, but makes a heck of a lot of difference when you're about 4 years old. I stress this because when you are deciding should something be atomic or should it be divided up, you are going to have to make design choices. Do I want to split up the birth date? Everybody assumes names should be split up. Most of the reason for splitting up names is because when we sort lists of names, we tend to sort them, at least in North America and Britain, based on the last name. There's no fundamental reason for sorting based on the last name other than the fact that that's what we happen to do. But more to the point, suppose I was keeping track of a database of names and addresses because I have customers and I want to send them mail. Not email, mail. Well, if I want to send mail to customers, I don't necessarily need to break down their address. All I need is just address so that it's printable on an envelope. All I need is their name so it's printable on an envelope. It's not necessarily the case that they need to be broken down. So, these issues are design issues. And that is a complex question, and it's a particularly complex question because here's my database. It has some names in it. It has some addresses in it, and whatever else it has in it. And I created my database because I have an application that is going to use that data. For example, I want to mail out information, so it's a mail application. Okay? But having created the database, someone says, oh, I'd like to use that data for a different application. What this means is when you are deciding atomic versus not, you need to think not just in terms of here's my application, you need to think of, here is my likely suite of applications. Okay. Now, you won't get that right. How do I know that? Because you can't predict the future. And there's a limit to how far you want to go. We'll have an example elsewhere in this lecture or in other lectures about where this becomes a very relevant issue as to whether or not you should divide things up. But I want to make sure that you understand that although this is superficially a very simple concept, in practice the design decisions you make are not obvious at all. And you really want to document your design decisions and justify your design decisions. Okay, so let's think of an example of a couple of entities, a UW student, a UW telephone. So a UW student might have a student ID, last name, and here's an example of breaking things down. First name and initial. This is exactly what is stored in Quest. Okay, when I see the set of students in the class, there is last name and there is first name and initials. These are not done as separate attributes. Okay? The degree, program, term, admitted, user ID, email address, etc. Okay. Then you might have another entity, telephone. Has an extension, whatever, 33333. A type, it's a Nortel X259, whatever. Okay, it's in an office number, E74666. For example, one can imagine, I have no idea whether any of these places exist, hopefully not. The point is, you can imagine all of these things having particular values. Now, a question you should be asking yourself is, should a telephone be an entity or an attribute? And that's a design issue. And we will look at that particular design issue later. But very briefly, should something be an entity or an attribute? It depends on what you're trying to achieve. If your objective is fundamentally about a student database and you simply want to keep track of their telephone, you can have a telephone number here. But imagine you, instead of having UW student, you have people. Not everybody necessarily has a telephone number that we're aware of. In fact, the university probably doesn't even care about most people's telephones. But they probably care about University of Waterloo telephones that are sitting in offices. And some offices are shared. Some offices are individual. If an office is shared, then having a telephone here is a problem, because that means we've got the same telephone number listed twice, whereas here we would simply say, nope, this is the office and the telephone number. Okay, how do we set up keys for these, or why do we set up keys for these? So this is similar to what we've described earlier about keys in the relational model. A superkey is a set of one or more attributes whose value uniquely determines each entity. And how do we know each entity must be uniquely determined? Because an entity is defined as distinguishable from other entities. So if you cannot distinguish it on the basis of the attributes that you have, then you don't have a sufficient description of your entity. So there must be some subset of the attributes, possibly it requires all of them, but some subset of the attributes that is necessary to uniquely determine an entity. A candidate key is any minimal superkey where minimal simply means remove any attribute and you no longer uniquely identify each entity. Now this is slightly misleading. Let me give you an example. DNA. DNA uniquely identifies people, except when it doesn't. There are these little beasties called identical twins, which have, well, identical DNA. but they're still distinct entities. Okay. Harry Potter, Fred and George, they might be identical twins, but they're different. Okay, so let's chop the ear off Fred, and then we can tell the difference between them. Okay, maybe we should not do that, but the point is, there needs to be some other attribute. But that doesn't mean DNA doesn't kind of uniquely identify most people. That's correct. It does identify most people. So when we say something is a candidate key because any attribute being removed will not uniquely identify each entity, you could literally have an attribute that is needed to simply distinguish two entities out of a set of 20 million, and without that particular attribute, every other entity is distinguishable, but those two are not distinguishable just because of that one attribute. Okay? So it doesn't mean that you can't identify most entities. It doesn't even mean that you can't identify all but two of the entities. It means precisely that every single entity has to be distinguishable. And if there are even two entities that are no longer distinguishable because we're missing an attribute, then that attribute is needed for the key to be minimal. Okay. So, and frequently we will create IDs in order to identify unique items that will automatically label things. So course ID, ID of an instructor, student ID, these are all things that will be used to uniquely identify. Okay. Several candidate keys may exist. Okay. There was a time when Yelp only allowed you to give one review for a business. If you changed your mind on the business, you could update your review, but you could only give one review. If you can only give one review, then the business ID and the user ID will uniquely identify the review. There is, of course, a review ID that also uniquely identifies the review. Both of those are candidate keys. This one's smaller than this one, doesn't matter. Both are minimal because they don't overlap, and if you remove review ID from this, there is no key. If you remove either of these attributes, you no longer can uniquely identify the reviews. Notice, by the way, you would still be able to uniquely identify reviews from users who have done only one review or businesses that have only received one review. So again, this is my point. There are many things that can be identified based on this subset, but you can't identify every single one. One of the candidates is selected to be the primary key. Which one is a design decision? And it is typically the case if you created an artificial one for that purpose, you will typically have that as your defined candidate primary key. Now let's look at relationships. A relationship is an association between two or more entities. For example, Kleiner advises Einstein. For those who don't know, Kleiner was Einstein's advisor in university. Fred borrowed War and Peace from the Kitchener Library. And for those who didn't get the point about existence, in our world, 3 and 5 both exist. You might say, of course they exist, and I'll say, no, of course they don't exist in the real world, because nobody can show me 3. You can show me 3 of something, but you can't show me 3. Can't show me 3 fingers. You can show me 3 fingers. You can show me 3 apples, but you can't show me 3 in the abstract. Anyway, 3 is less than 5. It's a relation. Okay? A relationship set is a mathematical relation among multiple entities. In this particular case, n. And we create a tuple where E1 comes from the domain big E1, E2 comes from the domain big E2, etc. And so this is our set, or if you prefer the standard cross product notation, the relation is a subset of E1 cross E2 cross E3, etc. So if we were describing these three in relation terminology, we would say Kleiner, Einstein is an element of advisors. Fred, War and Peace, Kitchener Library is an element of borrows. 3, 5 is an element of less than. Okay. We asked the question earlier, should we have an entity or an attribute in the context of telephones and telephone numbers? We can ask the same question here. Should we have a relationship or should we have an attribute? For example, suppose every student is required to have an advisor, but they're required to have precisely one advisor. We could have a student entity that has an ID and a name and whatever else, and somewhere in there we can have an advisor attribute. Okay. Now, in an ER model, this is probably not the right choice for this particular issue. And the reason is very simple. An advisor is something or someone who has properties in and of themselves. Somewhere else we're going to have an instructor relation, and an instructor has an ID and a name and whatever else they have. And we would like to connect the concept of student with the concept of an instructor, and we would like to connect those two with an advising relationship. Whereas if we have this attribute here simply as an attribute, then we lose this connection. And so if the attribute that you're considering has properties in and of itself, or would have properties in and of itself, would have attributes in and of itself, it's probably better to have a relationship. If it doesn't, or it does but you don't care, for example, cell phone number. We probably don't care that it's a Samsung phone, and we probably don't care that you bought it 3 years ago, and we probably don't care the condition of the screen, and we probably don't care what version of the operating system you're using. We probably only care about the phone number to contact you. In that context, make it an attribute. So, should something have a relationship or an attribute? It's essentially the same question as should we have a separate entity or should we have it as an attribute. Now, here's some illustrations that come from the textbook. Here's an example of an instructor-student relationship. Now, note, this is not an ER diagram. This is not pretending to be an ER diagram. It simply is just a diagram intended to show the relationship. So Crick advises Tanaka, Kantz advises Shankar and Zen, Srinivasan advises Brown, Kim advises Oi, etc. A relationship set might have attributes of its own. There are no attributes. It's just saying this instructor advises this student. Well, since when? Forever? Have they always advised them? Will they always advise them? Maybe we want to add an attribute. This is the point at which Crick started to advise Tanaka. This is the point at which Katz started to advise Shankar. This is the point at which Katz started to advise Shang. We can have multiple descriptive attributes, by the way. So this would be starts. One could also have terminates, which would actually be another set of attributes, which would be Crick was advising Tanaka starting on the 3rd of May 2008 and finished on the 9th of December 2009, indicating that the advising relationship had maybe successfully finished. Who knows? Okay. So do not believe that there is only one attribute. There could be multiple attributes. So now let's look at the degree of a relationship set. First of all, binary relationships. Now the textbook here says these are, quote, most common, and it says that these are rare, but they do exist. All I can say is I think the textbook is completely nonsense on this. There are a large number of reasons why you will have many, many n-ary relationships, and you will have binary relationships simply because they make sense as binary relationships. So, very good example, you might have a married relationship. Okay? A and B are married. Okay? It's inherently a binary relationship. Okay? An advisor relationship isn't necessarily a binary relationship. You could make it a binary relationship, but you could imagine a junior-senior advisory relationship. So you've got a junior advisor and a senior advisor, and then a student. Okay. There are many binary relationships, sort of, that exist. Any non-binary relationship, in principle, can be removed to a set of binary relationships, but sort of. There are some significant caveats to that, and we'll talk about that later. N-ary relationship is any relationship that involves more than two entity sets. It's sometimes referred to as a degree N relationship. They are more complex. This is true. It is certainly the case that binary relationships are the simplest and n-ary relationships are more complex, and the more entities there are, the more complex they are. The example given in the book, students work on research projects under the guidance of instructors. I've already shown a different example. Patrons borrow books from libraries. That's a ternary relationship. N-ary is the general term. Let me ternary, Q-U-A-T-E-R-N, quaternary, quinternary, but basically people just say degree 3, degree 4, degree 5. In terms of a 3-element relationship, student, project, instructor, these, for particular instances, will be elements of the guided work relationship. Okay, let's think about n-ary to binary transformation. Students work on research projects under the guidance of an instructor. First of all, why is this not the same as a binary advisor's relationship with an attribute? Okay, students are advised by an instructor on a research project. So we can imagine, I want to change this to blue. Here's a student, and they work with an advisor. And there is some research project. Okay. Now the first problem with that is, what if there's 2 research projects? RP2 for the same advisor. Okay. But there's a second issue about that. Research projects aren't generally things that necessarily have students to start with. Okay. A research project typically will have a principal investigator. It will typically have a budget. It will typically have funding support. Funding supports. So maybe there's company A, and there's NSERC, and maybe there's something else, and ORE. There are different sources of funding, etc. So a research project has a whole number of... it will invariably have a start date. It may have reporting obligations. People won't give you money just for the heck of it. Obligations, etc. So, simply labeling it as an attribute of the advisor-student relationship has a number of problems right there. Okay, multi-valued, but also it has attributes of its own. Okay, so this only works if the item in question can be reasonably reduced to a single attribute of interest in the scenario. Okay. Such as, for example, when you talk about the start of the advising relationship. Okay. Single attribute. Maybe you have the start and the termination, and those are a couple of attributes, but you don't really care about them separately. Okay, so you could imagine a student, advisor, instructor. You could actually imagine an advising relationship as a concept, as an entity in and of itself, which has attributes like start date, end date, status, is it going well, is it going badly, etc. You could imagine having that as an entity, and then you have this three-way relationship between these three entities. Okay. This is probably... Would it be necessary or not? It could be. One could imagine keeping track of these advising relationships. One could imagine this would be useful, building a record of sort of what are the nature of advising relationships. But in many scenarios, this would be overkill. It would be quite unnecessary to do. So that's an example where you could have an attribute. It is possible, but this is probably not that case. Okay, what about simply reducing it to three binary relationships? Students are advised by instructors, students work on research projects, instructors guide work on research projects. Now, here's the problem with that. You've lost the fact that those things are done in conjunction. The student isn't simply being advised by the instructor and independent of that working on the research project, and the instructor is independently guiding work on the research project. See, this requires no students, this requires no guidance, and this requires no projects. That each of those binary relationships has lost the totality. You are able to update them individually in a way that is probably undesirable. You could have an instructor working on a research project, pretending to guide research on a project, but has no students. You could imagine students working on a project with no guidance. You could imagine students being guided by instructors, but not on anything. The lack of combining them together is the problem. It amounts to people borrowing books without notifying the library, or libraries lending books without identifying the people that they're lending them to, etc. You've lost information. We now consider the issue of what are referred to as cardinality constraints. These constraints are nothing more than an expression of the number of entities to which any given entity can be associated. Now, first, let's clarify, these constraints reflect the possible structure of the data. They do not reflect that of a particular data set. That is not to say a particular data set can violate these constraints. It simply means that a particular set of data may be more constrained than is implied by the constraint. So let's consider an example. Every child has exactly one father, and we're obviously talking about a biological father here in this context. So every child has exactly one father, not two, not zero. A man, by contrast, could father more than one child, but may father no children. Okay, and note I'm saying man here, not father, because there is a difference. So the man-child relationship is what is referred to as a 0 to n relationship. A man may have 0 children, 1 child, 2 children, many children. The child-man relationship is a 1-to-1 relationship. A child has a father. A child-man relationship is a 1-to-1 relationship. The child has a father, male. The child-mother relationship likewise would be 1-1. The textbook would describe this as actually a 1-to-many relationship. I'll talk about why that is in a little bit. In this more precise terminology, the father-child relationship is 1-to-many, and the reason for that is very simple. A man can have no children or 1 child or many children, but in order to be a father, by definition, you must have had 1 child. If you haven't had any children, ipso facto, you're not a father. Again, mother-child relationship would likewise be 1-to-n. So we can consider other relationships. Every author has at least 1 publication, so an author-publication relationship would be 1-to-many. Okay. Every publication has at least 1 author, so a publication-to-author relationship would likewise be 1-to-many. Okay, let's make that M, because we're saying M and M have no relationship to each other. A publication might have 1 author, 2 authors, 5 authors, but an author doesn't necessarily have the same number of publications as the publication has authors. So, considering these two together, an author-publication relationship is n-to-n or many-to-many. Okay. Now, n may be replaced with a specific number if there is a known upper bound, or it could just be some undefined parameter, and if it's undefined, typically we will use asterisks. So traditional cardinality constraints. There are 4 of these. There is the so-called 1-to-1, in which both entities are in the relation, and this is where there's a difference, 0 or 1 time. So, as I said here, the text would describe a man-child relationship as 1-to-n, the reason being every child has a father, every man... If we have a man-child relationship, a man may have 0 or it may have 1 or 2. Every child has exactly 1 father. Okay, so this would be described as a 1-to-many relation. Okay, a 1-to-1 relation, something like marriage would be a 1-to-1 relation in the textbook. Any man might marry any woman. Actually, we could just do person to person. Let's not get into that political debate. The one-to-one relation in marriage simply reflects the fact that there are two people in a marriage. There are not more than two people, at least generally speaking. A one-to-many relationship or a many-to-one relationship, one of the entities is in the relationship either 0 or once, and the other entity could be 0, could be once, could be many times. And then we have what is referred to as the many-to-many relationship. Both entities are in the relationship 0 to many times. This is unconstrained. Okay. These, I have said, are the traditional cardinality constraints. This is what the textbook describes. There are serious limitations in this approach. They are upper bound only mappings. So when we say something is in a one-to-one relationship, it means it is at most once, but it could be 0. So it expresses the upper bound for that relationship. It doesn't express whether or not participation is not possible, or it doesn't specify the requirement. So there is no lower bound. There's no 0 versus 1 option. Okay. Both upper and lower bounds are limited to 1 or infinity. There is no limit on the lower or upper bound. And there's a really good example of this. A very common requirement in business, for example, for signing checks or signing checks for a certain amount, would be 2 signatures are required. There is no 2 to n requirement. A peer review in a coding exercise, you may require at least 2 peers. The idea that there might be more than 2, not something that's in there. And in particular, when 2 signatures are required, these are not usually ordered signatures. So you can't describe that and say, well, there's 2 separate things. There's signature number 1 and signature number 2. Those can be arbitrary order. So 2 signatures required is not the same as signature number 1 is required from person 1 and signature number 2 is required from person 2. And in fact, later we'll see where that becomes an issue. So the traditional mapping of cardinality constraints, we've got a couple of entities. So this is a one-to-one relationship. Okay, and notice that this entity in set A is not mapping to any entity in set B. Now, by the way, there's nothing that says it couldn't, for example, do that, except that wouldn't be one-to-one anymore, because this entity would then be mapping to 2 different ones in A. So that wouldn't be possible. Omitting 1, perfectly fine. So this omission is okay, but it cannot have duplicate. This is a one-to-many. Okay, we'll leave that there. Because these entities may map to more than 1 in the B. Okay, but each B maps to only 1 A. This is an inverse of this, many-to-one. Okay, and then finally you have many-to-many, in which there could be multiple mappings. This is mapping to B1 and to B2, and B3 is mapping to A3 and A4, so we have many-to-many. Okay. There's better cardinality constraints, and I would like you to use these. They are much more precise. So the first thing is we want to specify lower as well as upper bounds for each entity, and we want to do so to each entity within the relation. So the way these work is it's about the 2 entities. Call them E1 and E2. Actually, let me flip over to my whiteboard. We've got E1 and we've got E2, and we're trying to see how they're related to each other. But instead, with this better approach, what we've got is we've got E1 and we've got E2, or maybe even E3, because we could have more than 2 things in the relationship. And what we're doing is we've got this relationship and we're saying, How many times is E1 allowed in the relationship? What's the lower bound? What's the upper bound? Okay. How many times is E2 in the relationship? What's the lower bound? What's the upper bound? So it's about the number of times each entity is allowed in the relationship. So if we talk about, sorry, I don't want to say father, I want to say man, we'll be clear on this. Suppose one is man and one is child. Okay, and the relationship is father, something like that. Man is father of child. Could be 0, could be any upper bound number. Child, how many children are in how many children have more than one father? Exactly 0. You have 1 is the lower bound, 1 is the upper bound. So this is the concept that we're dealing with. So if we go back here and we look at these beta cardinality constraints, numbers, it's usually best if it's 0 or 1, occasionally some other numbers. And when I'm saying numbers, I mean numbers, not parameters. Parameters, so that would be maybe n or m or whatever, those allow us to specify a number that can be a design parameter. So let me give you an example. Suppose we want to allow checking out books from a library. So we've got people, and we've got books, and we've got library, various libraries, or library branches, or whatever, and we want to check out books. And we say people can check out books, books can be checked out, and libraries can have books checked out from them. Okay? How many books can a person check out? So I want you to think here for a moment. Let's imagine we just talk about checking out a book, and we forget about the library bit. A person can check out a book can be checked out. How many times does a book have to be checked out? Well, it might not be checked out at all. But if it is checked out, then it can't be checked out by somebody else. Checked out is checked out. It's out. Okay? A person might check out no books. Can a person check out an unlimited number of books? No, they can't. Libraries invariably will have some upper limit on how many books you're allowed to check out. Otherwise, I'm going to go to the Library of Congress and check them all out. There's like about 15 million books there. I'll take them all, thank you, and leave. Okay? So there is invariably some upper bound. And so when I say we can specify a parameter in a constraint, we can say n, we say n maximum number of books that can be checked out. Okay. And this is important because if we're doing an entity relationship model, we want to be able to say things like, okay, people check out books, and we want to say a book might not be checked out, or it might be checked out exactly once if it's checked out. Now, a book could be checked out multiple times at different dates. So we can have, on Thursday the book's checked out, it's returned, and then on Friday it's checked out. So we may have some ability to do this multiple times, but at any given time it can only be checked out once. So it's not checked out, or it is checked out. A person who's got a library card may not check out any books. The most they can check out is n, and we specify n as a parameter of our model. So again, we've already got something better, and this is why numbers, usually best if they're 0 or 1. Occasionally they're okay if they're the different ones. The classic example being 2 signatures being required is something that might be hard-coded as a number, although even there it would be better to have a specification. S signatures are required and it can be defined. So parameters, much, much better. Asterisk means there is no specific bound, okay? No specific lower bound, no specific upper bound. So, for example, if we say, let's say you can, an instructor can advise students, is there a limit to how many students an instructor can advise? And you might make the argument that there would be a good policy reason to limit that number, but actually there's also a good reason to not limit that number. So, for example, if we require every student to have an advisor, it may be the case that the associate chair for graduate studies winds up being the default advisor for any student who doesn't have an advisor. Now, if you've got 500 graduate students in the department and a large number of them are coming in without a formal advisor, having the associate chair defined as that person is useful. You probably don't want to specify that as a number. So, there may be no upper bound. So, given these constraints, what are the options? Well, 0 to 1. Participation is not required, but if it is there, it's exactly once. Okay, so an example of this, married. Okay, you are either in the relationship, you're married, or you're not married. Don't get into divorce and remarriage. It still winds up being in exactly the same situation. You're not allowed to be in the relationship married twice at any given time. Okay. 0 to n, participation is not required, but if it is, it's at most n times. So this is our example of the library checkout. You don't have to check out a book from the library, but if you do check out books from the library, at most n of them at any given time. 0 to many, advisors don't have to supervise students, but if they do, there is no upper bound. Okay. Then we deal with the ones as the lower bound. Whenever 1 is a lower bound, we're 1 to 1, 1 to n, 1 to many, the entity must be in the relation. So this means it's a required participation. Okay? An example of this would be something like, a student must have an advisor. This says a student must have an advisor and must have exactly one advisor. 1 to n, a student must have an advisor, may have more than one, but can't have more than n, where n is some parameter. So you might imagine an advisor relationship that says 1 to 2, for example. A student must have an advisor. They may have a second advisor. You can't have more than 2 advisors. Okay. 1 to many. This is an example of you must be in the relation and you can be in the relation multiple times with no upper bound. A student is required to take at least one course, and they can take as many courses as they like. Okay. N to M, this is the student must be in the relation. I'm assuming N here is greater than 1. If N is less than 1, if N is 0 or 1, you would use 0 or 1. So implicitly, whenever we have a parameter, it's bigger than 1. So this situation must be in the relation at least n times and at most m times. For example, you might say something must be reviewed. There must be at least this number of reviewers, and we don't want more than some bigger number of reviewers because then we're wasting resources. It's pointless, for example. N to star must be in the relation at least n times. So there is a lower bound, there is no upper bound. And then finally this many to many, there is no limit on participation, anything from 0 to infinity. This is an unconstrained situation. And if you think about it a little bit, this is essentially identical to 0 to many, because if the lower bound is 0, that's the same as the lower bound is undefined. Okay, cardinality constraint limitations. Traditional cardinality constraints are only useful for binary relationship sets. So, for example, a parent-child relationship or a advisor-student relationship. It is not feasible for expressing any ternary cardinality constraints or anything beyond ternary. So what's an example of a ternary one? This is an example of a ternary one. People check out books from libraries. There are 3 elements in the relationship. Okay. The traditional constraints can't express anything beyond binary. Why not? Here's why not. Suppose we have book and person and checkout. Well, what we're expressing is the cardinality between these two. So a person may check out 0 books or 1 book or 2 books or many books. Books can be checked out in some number. So there's many books that can be checked out, but a book can only be checked out once. If it's checked out, it's checked out. Until it's returned, of course. So it's a one-to-many relationship. We're expressing this relationship between these 2 entities. As soon as we say there's 3 entities, and we're doing checkout, and we say one-to-many, well, we've got books, we've got libraries, we've got people. Is the one-to-many between books and people? Is it between books and libraries? Is it between libraries and people? We don't know which it is. There are, in fact, 3 separate things here. So, this is an intrinsically hard problem. There is no formal way of specifying it, or at least there's no agreed upon way. It is almost invariably the case that you would not want to illustrate this in a diagram, and we'll come to entity relationship diagrams in a bit. You almost certainly would not want to illustrate this in a diagram. It would be messy, it wouldn't be helpful. But if we use those better cardinality constraints, we can in fact very easily express this. Let's consider a relationship. Students work on research projects under the guidance of an instructor. Okay, so remember, italics is a relationship set, red is an entity. So we've got 3 entities and we've got 1 relationship. It says under the guidance of, but fundamentally there's 1 relationship. We've got students, research projects, and instructors. They are collectively combined together. And we do not want to decompose them into binary relationships. That's fine, but that doesn't mean we can't consider the binary pairs and their cardinality constraints. So let's imagine we have this situation. Students must have an advisor, but may have more than one. And they must have a designated research project. Okay. Instructors, not required to advise any students, but if they wish, they can. They're not required to have any research projects. Implicitly, they can. Projects must have a designated PI. That's a principal investigator. That's an instructor. They may not be staffed. So there may be students on the project. There may not be students on the project. So what does this mean? Well, consider the binary pairs. Student-instructor relationship is 1 to many. A student must have an advisor, but may have more than one. Must have one, may have more than one. An instructor is not required to advise students, but if they do, they can. They can if they wish to. So, not required to advise, but they can if they wish to. And it's students plural. They can advise 1, 2, many, or none. An instructor is not required to have any research projects, but they can obviously if they want to. So again, 0 to many. So instructor project is 0 to many. Project instructor, each project must have a designated PI. And the fact that it's called a principal investigator is precisely the fact that there may be many other investigators, but there's one designated principal investigator, so that's a one-to-one relationship. The project has a designated instructor associated with it. Then finally, student projects. Student project is one-to-one. A student must have a designated research project. So if a student is going to come to the university, they must work with an instructor and they must have a project. Project to student. Projects may have no students. I've put M as the upper bound. Almost invariably, every project has a designated maximum number of people associated with it, but this could just as easily be star. This would be a function of the nature of the project. So, standard traditional terminology can't be done. If we use these better constraints, and the textbook talks a little bit about them as alternatives towards the end, unfortunately they focus on the traditional constraints. So do look at these better ones. They are to be preferred. Okay, let's talk about keys for relationship sets. We've already talked about keys for entity sets. Well, relationship sets. A relationship is the combination or the connection of multiple entities to each other. So, first point, the primary keys of the entity sets that are combined by the relationship form a superkey. So these primary keys form a superkey. So if we go back to this, books, let's say each book has a book ID. It'll be a ISBN or whatever. Let's say every library has a library ID and every person has a person ID. So if we want to talk about what's the primary key of this relation, well, a superkey will be BID, LID, and PID, the person ID, the library ID, and the book ID. Okay, so the primary key will be that or maybe less than that. This is assuming that the relationship has no attributes. If the relationship has attributes, it will depend on the nature of the attributes. So if we think about the advisor relation, student ID and instructor ID are a superkey of the advisor. Now, a couple of points here. First of all, dotted notation resolves the naming collision. Okay. However, in a relational database, you won't be able to use dotted notation for an attribute. This is an ER model, entity relationship model. It is not a relational schema for a relational database. This is the key for a relationship set in an entity relationship model. So that's common to use in an ER model, dotted notation, to avoid name collisions. Two entities can be in a particular binary relationship set only once. Why? Well, for starters, because that's the key. And more to the point, that's the point of the relationship. Okay. Notice this is true whether we have one-to-one, many-to-one, many-to-many. So let's think about this for a minute. We'll go back to blue one here. Okay. Suppose I have advisor and student. Okay. I suppose a student can have as many advisors as they like. Advisors can have as many students as they like. They can have none. So if we think about it, we've got an advisor ID. We've got a student ID. Let's say Fred is ID 123, and he's advising student ABC, and he's also advising student DEF. Okay, and maybe we've got Mary. She's advisor ID 456, and maybe she's also supervising ABC. Okay. What would happen if we had 1, 2, 3, ABC a second time? Well, these are duplicate entries. Okay. No duplicate entries allowed. Again, remember, we've got no attributes in the particular binary relationship. Okay. If there are attributes, it's possible that we can have it more than once, and there'll be a reason why. So what this means is, suppose we have meeting, student, and advisor. Even that one, which has a date for a meeting, the date is a single valued attribute. So it doesn't help us. Okay. Having the single valued attribute, we extend with date here. Okay. Well, 1, 2, 3 started supervising on whatever date. And it's still the same date. Okay. We don't have it more than once. However, we can have multi-valued attributes. So if we had a multi-valued attribute meeting time, and let's just say date, and we call that a multi-valued attribute, now that can be in more than once. Okay. So, broadly speaking, if the relationship set has attributes, a superkey is the primary key of the entity sets together with the attributes. Well, we can do better than that. That is a superkey, and we want a candidate key. Actually, we want a primary key, and we can do better. I've already shown an example. If it is a single valued attribute, you do not need the attribute to form part of the primary key. The primary keys of the entities are sufficient. So let's think about cardinality constraints and relation keys. First, let's consider the zero attribute relationship set. So we'll avoid attributes. So we'll imagine we just have an instructor and an advisor or a married couple. Okay. Married couple is a good example. People can be married or not married. Okay. Broadly speaking, if people can be married or not married, the relationship is a 0-1 on the part of both parties. Okay. A 1-1 relationship, an example of that. A normal checking account. A normal checking account requires exactly one signature. So you have to sign the check, and the check has to be signed. So the relationship between the check and the signature is 1-1. The check must have exactly one signature. So that's 1-1. So married is a 0-1 relationship. Married, AB. And in this particular case, either party can be the primary key. You don't need both. Let me give an example. So you have this people relationship, entity, okay, which describes people. It has an ID and a name and whatever else. And you have the is married to, okay, and people are married to other people, obviously, okay, and this is a 0-1 relationship. People are married to other people, or they're not married at all. They're married to exactly one other person. It doesn't matter. So this is effectively person 1 and person 2. It doesn't matter which one is the key, because if person 2 is Fred, let's say, well, Fred can't also be in here a second time. Why not? Because Fred is married to whomever here, and Fred can't therefore be in the relationship twice. Okay, again, no extra attributes to help us. Okay. So 0, 1 or 1, 1, either party can be the primary key. Either entity can be the primary key. Okay, what if it's a 0 to n or 0 to star or 1 to n or 1 to star, and the other entity is a 0, 1 or 1, 1? So in other words, in traditional terms, this is a one-to-many or a many-to-one relationship. In that particular case, whichever is the 0 to 1 or the 1 to 1 entity, that suffices to act as the primary key. Okay? So let's say every student either doesn't have an advisor or has at most one advisor. So the student is 0, 1, and the instructor is 0 to many. In that particular case, we have this advisors relation, and what we're going to have is the student ID will be the key, and the instructor ID will be there, but it doesn't need to be the key. This will be the key, and the reason is if it's in there, it's only in there once, whereas the instructor may be in there more than once. Okay? If neither of these conditions is true, then the primary keys of both entities are required to form the primary key of the relation. Okay? Or the relationship set, to be precise. Okay, what if there is an attribute? Well, we'll start with a single attribute. If it's a single valued attribute, the above rules apply. It makes no difference. Okay? Any particular combination of entities can only appear once. Okay? But if it's a multi-valued attribute, then the attribute has to be added to whatever the situation is above in order to form the key. So let's imagine we have our student-instructor relationship, and, let's not make it advisors, let's make it meets. Okay. And we have student, and we have instructor, and we have time, or date time, whatever. Whatever it is, it's the meeting time. If we have the student as having either no advisor or one advisor, then this isn't needed, okay, because the student has exactly one. This is needed, but this is also needed, and the reason this is needed is because it takes on multiple values, and so it allows the instructor to have multiple separate meetings. If there are multiple single-valued attributes, well, the above rules still apply, because whenever we have single-valued attributes, whatever the relationship is between the two entities, these will all take on the same value, so they provide no additional information in terms of a key. They're not needed. What if there are multiple multi-valued attributes? Okay, I've put you should probably reevaluate your design choices, and that is probably true. Okay. In particular, we have a relationship, and it has call them attribute 1 and attribute 2 and attribute 3, and this is multi-valued, and this is multi-valued, and this is multi-valued. This is probably a bad design. Either these are connected or they're not. Imagine you had a shopping relationship. A customer is buying something from a vendor. So you want to keep track of the date, you want to keep track of the time, you want to keep track of the price, you want to keep track of the quantity. Okay, so there's all of these attributes, and you have a vendor ID and you have a purchaser ID. Okay, so these on their own, a purchaser purchases from a vendor. They can purchase from one vendor. They can purchase from many vendors. A vendor can sell to multiple customers. Actually, I shouldn't call it purchaser. Let's call it customer. It'll be clearer. So we'll say customer. Okay, so both of those are required. If you want to ever do more than one purchase, well, the date has to be multi-valued, and the time, and the price, and the quantity. These all have to be multi-valued, and you say, ugh, I'd like to be able to do that, but you've just told me to reevaluate my design. Well, there's one way I can reevaluate the design, and it works. These are all intrinsically a single thing. They're DTPQ. Let's call them that. The date, time, purchase, and quantity, they can form a single composite attribute. Okay? And the date, time, purchase, quantity consists of the date, the time, and the price, and the quantity. And the important point is this is single value, this is single value, this is single value, this is single value, this is multi-value. Within any given instance of this, there's only one of these. So these things are bound together. So in that sense, we have a single composite multi-value attribute. So if the attributes intrinsically can be combined together in a way that makes sense, then that is in effect a single attribute that's multi-valued. And that's fine. And we can simply make that part of the key. If they are not intrinsically able to be attached to each other, you really should seriously reevaluate your design. And there are design issues that I will talk about.